Good afternoon, ladies and gentlemen. So we're here for the last session of the evening, for the afternoon of the Faculty Summit. And it is a lead up to our great DemoFest, which will happen straight afterwards. And of course, because it's DemoFest, it is absolutely fitting that it should be introduced by the head of the Redmond Lab, who is Peter Lee. Peter Lee is managing director and also a distinguished scientist, one of our top people in Redmond. And before he came to us, he had an academic career. He was head of Department of Computer Science at Carnegie Mellon University. And his area there was programming languages, compilers, and so on. Many of you probably know him from those days. In between his stay at Carnegie Mellon and here, he was also at DARPA. He had a while in DARPA where he was solving problems for them, where he was an officer manager. But he tells me that that's actually the equivalent of a general. So at this stage, I'd like us all to welcome General Dr. Peter Lee.
So thanks, Judith. It's really it's a thrill to be here. After years of coming to the Faculty Summit as a faculty member, it's strange and wonderful to be on the other side of this, and I'm getting a newfound appreciation for how much goes into this kind of event. I thought a lot about what to say here, and what I wanted to do was to talk about my recent journey. I have been on a journey over the last few years, going from completing the trifecta, going from academia to government and now to industry. And from that, I've gotten a little bit of a different perspective. My perspectives about computer science research and research in general have changed a lot, and I thought I would try to express some of that, and also to give it in a way that would, in at least an underhanded way, allow me to brag a little bit about some of the great stuff going on in our lab. And so let me dive right in. So it's a journey. I'm going to start a little bit autobiographical here. Now, I grew up in a household. I had a physics professor as a father and a chemistry professor as a mother. You might imagine that computer science definitely was not respectable in that household. And in fact, computer science, especially in those days, and especially amongst physical scientists, was really viewed as a tool, not really an intellectual pursuit or an academic profession on the same level as the great physical sciences. And so I ended up going to college and majoring in physics at the start. And then later, when I realized that wasn't for me, I disappointed my parents and majored in mathematics. Now, of course, all the time, and even in high school, I was attracted to computers and to computer science. And an important thing happened to me as an undergraduate, which was I ran into the work of the man you see pictured here, Dana Scott. And Dana, as many of you know, was a very important computer scientist, is a very important computer scientist, and at Carnegie Mellon, of course, and prior to that at Oxford, had done some very important work in developing the foundations of the formal semantics of programming languages, and ideas like domain theory and denotational semantics, along with collaborators like Christopher Strachey. Now, I try to explain to people what this is all about, and even computer scientists, working computer science researchers today, don't have a very clear concept about this. And so I have a standard explanation for this, which is actually a textbook explanation. So if you pick up a standard textbook on formal semantics, you'll see this example. And so what is this about? And how did I get introduced to computer science this way? Well, let's take this very simple thought experiment. We see here an equation. Now, all of us as computer scientists would see this and understand this as a program immediately, a program to compute factorials. But as a mathematician, I didn't see this as a program. This is just a mathematical equation. And in fact, it's one that implies a problem to solve, namely to solve for the unknown f here. And so there is nothing, at least to a prejudiced mathematician, as I was in the early days, nothing special about computer science exposed by this piece of code. And in fact, it's not too hard to see that if we solve this by using God's factorial function, we can see that the equation holds and everything is just fine. Now, the early work of Dana Scotts and others in the time, in the late 50s and early 60s, started to realize that there were certain conundrums, certain paradoxes here. So, for example, there are other equations that don't correspond to sensible programs for which sensible functions like the factorial function still are solutions. And in this kind of situation, suddenly, at least in the conventional mathematical thinking of the day, something is very odd. And this launched a long series of very important research, and ultimately a Turing Award and many, many other kinds of follow-on pieces of work. And for me, this was a revelation. Suddenly, it was a realization that there was something much more to computer science than would meet the eye of a mathematician or a physicist or a chemist. That there was actually a new intellectual pursuit, something that hadn't been contemplated before by man. And for me, this was the top cover I needed, the reason that I needed to finally fall into being a computer science researcher. And I ended up switching and going to graduate school for computer science. Now, this informed my research then after my PhD studies as a young assistant professor. And for me, this is a kind of research that is just achingly beautiful. Just has this crystalline structure. And if this isn't the right way to think about computer programs, then that's a cruel hoax played by God or somebody to just give us such beautiful things and not have this be the right way to think. And this was really something that shaped my early research at Carnegie Mellon. Of course, this is also, as many of you I'm sure have experienced in your own careers, when you are really committed to foundational research in computer science, you sometimes have a hard time convincing colleagues or funding agencies or review panels that what you're doing is valuable. And even for me, as a young professor, sometimes it was hard for people to understand the value of doing this kind of research. And so one of the themes that I'll be presenting here today is the value of fundamental research in computer science, and the fact that over and over again, since we're dealing with man-made artifacts, over and over again, these fundamental ideas end up down the line having tremendous practical impact. And in fact, today, of course, we now know completely well just how important some of those fundamental ideas in formal semantics of programming languages have been in the development of tools that are used every day now by millions of developers around the world to help make our software more secure and more reliable. And this is something about the science behind the demos. And so we will be introducing you all to the DemoFest after this, and the DemoFest has lots of cool, whizzy-looking demos. But we all have to remember and remain committed to the idea that behind those demos, there's a deep science that forms the foundation of these things. And that science is absolutely essential in everything we do. It's essential to everything we do here at Microsoft Research. Now, as Judith mentioned, I went from academia. I was there for 22 years at Carnegie Mellon, eventually the head of computer science, and then I went and had a short stint as an office director at DARPA. And DARPA even expanded my vision and my view about computing research even further. And in DARPA, there's really a tremendous diversity of different kinds of research, where if we look at the lower left of this diagram, where there are research programs that are fundamentally mission-focused. In other words, research that is designed to solve somebody's problem today, some crucial problem today. Two, moving to the lower right, research that has a component of sustaining our capabilities, constantly improving what we're capable of doing, constantly ensuring that we as a society have the capability to do certain things, almost as an insurance policy in case it should become needed at some point in the future. Two, continuing commitment to blue sky theoretical research, or even systems-oriented research that is just purely exploratory. And also, very much present, very strongly present at DARPA in the upper left, is a kind of wacky side of research where you're just trying to do something very inventive and new in the attempt to disrupt or surprise. And this type of search for disruptions in the short term, that's a big part of DARPA's mission to avoid technological surprise, kind of completes this picture. And so, taking all of these experiences together, I arrive at a map for computing research. And if we view this in two dimensions, on the x-axis, you go from research activities or projects that have spanned short-term hope or expectation for short-term payoff, and then as you go out the x-axis to long-term kinds of activities that may require some patience. And then on the y-axis, you go from reactive problems where somebody, society or someone here in Microsoft in a product group comes to us and says we need help solving a problem, to a more open-ended search for truth and beauty. And in this space of computing research, we see, if we divide these things into quadrants, a tremendous diversity in the kinds of things that go on in computer science. And so we see, just as I've drawn from the DARPA and Carnegie Mellon experiences, mission-focused, sustaining research, blue sky research, and disruptive research. And this quadrant diagram, which actually is not purely my invention, but was inspired, not exactly in this form, but inspired by a person at DARPA named Peter Zatko, who's also a fairly famous and somewhat notorious former black hatter, has been a map that I use to understand, are we fully embracing the full diversity of possibilities in computing research? And here at Microsoft Research, to all of our research groups and research areas, I ask the question, are we making an impact across all four quadrants? Are we fully valuing and embracing the possibilities in all four quadrants of computing research? And so the journey through academia to government to here, really, if you wanted to sum it up, is summed up by this diagram. And so for me, I am always hungry for things to brag about in all four of these things. Now, I show this and link this back to the title of this talk, neither basic nor applied, because when you are in a government research agency or at a university, there's always talk about basic versus applied research. And that's the way that my parents would talk as physicists and chemists. Because in physics and chemistry, there is a real difference between basic and applied research, and a real difference between basic researchers and applied researchers. My claim is that in computing research, this distinction doesn't make any sense. And I believe any one of you would be hard-pressed to pigeonhole yourself as either a basic researcher or applied researcher. And so for all the demos you're about to see, and for all the things that you use, like search engines or Connect devices or any kind of smartphone or tablet, for all the applied things you see there, by and large, the computer science that went into these things had elements that you would call either basic or applied, but they're really impossible to separate. So I'd like now to go around these four quadrants and show some of you, by using examples from Microsoft Research, what is meant by mission-focused, sustaining, blue sky, and disruptive research. So let's dive right in. So I'm here now at Microsoft Research, completing the trifecta. All right, so let's start with mission-focused. So if we look on this map, we're in the short time scale. Problems that we want to solve, where the solution is needed now, or where the solution would really only make sense in the relatively short term. And in the reactive problem domain, meaning that these are problems that someone comes to us with or can state for us very clearly that need to be solved. And so how do we do that? Now, we do a lot of mission-focused research at Microsoft Research. One thing that Craig Mundy alluded to this morning, for example, is a societal problem about, in the healthcare IT domain, about readmission to hospitals. This is a very, very big problem that's pertinent to us right now. In fact, it informs part of the big budget debate in our country. Because one thing that we now know is that very large percentages of patients who have been hospitalized are readmitted to that hospital within 3 months after discharge. And oftentimes, and in fact the purpose of this paper that appeared in the New England Journal of Medicine is to show that sometimes even relatively cheap interventions, if we had known ahead of time that patients were susceptible to being readmitted, even relatively cheap interventions before discharge could have prevented a large number of these readmissions. And so the estimated cost of this problem is in the many billions of dollars. And so as Craig described this morning, this is an example of a kind of mission-focused problem that we here at Microsoft Research have devoted a lot of energy to addressing. But to get into more technical detail, beyond this predictive analytics from healthcare IT, let me introduce Chris Burgess to come and talk to you about some of the science behind search quality in the Bing search engine. Chris?
Much, Peter.
Great, thank you.
So I'm going to tell you about the algorithms that Bing uses to search, to order the search results. This is the task we're trying to solve. A typical query might be learning to rank. And I'm particularly interested in the second item that showed up, the Yahoo Learning to Rank challenge, which is a challenge that took place last year. It was a public challenge, and using a blind data set. About 1,000 teams took part. I'm surprised that many people work on this stuff, of which 312 were serious, and that they had 2 submissions. The system I'm going to tell you about today won that competition, and the reason I mention that is to show you that it's a competitive system, and it's entirely published. Everything that we do is published. The second interesting thing that shows up is the class of algorithms that we invented to solve this problem called lambda rank. And before I describe that, let me just describe the problem a little bit more. So how do people measure relevance? They have humans label the relevance of a bunch of documents given a query, and then based on the rank at which the documents appear and the labels, they'll give you a measure. And there are many different measures. I counted 15 at one point. So one of the things that lambda rank has to solve is how to solve the problem for any particular measure that anybody wants to solve for. And secondly, these measures are very discontinuous. If you change the scores a little bit, the ranking changes. The measure changes by a discrete amount. They're not differentiable. So it's a hard problem. Lambda rank was used by Bing beforehand, instantiated in neural networks. Today I'm going to tell you about the same algorithm, but instantiated using boosted trees, another kind of machine learning system, which is 100 times faster than the neural nets they replace. And this is essential for increased experimentation, which is really where the new relevance comes from, allowing people to try ideas quickly. So let's just show you how lambda rank is trained. Take a query, 1077.7, the end, which is a Seattle radio station. And imagine that we have these URLs, human-attached ratings or judgments. And let's suppose that we're in the middle of training and the model has come up with these scores. So first, we're going to reorder the scores. So it's not doing too well right now. It's putting a badly relevant thing at the top and a perfect lower down. What we'd like to do is somehow treat these URLs as point masses and attach forces to them. So here we're going to do that. We're going to say there's a force, pairwise force between each pair of URLs with different labels. And this, the good and the other good, the bad and the other good have a bigger force because the gap in the score is larger. An even bigger force here because a perfect wants to go up more and a bad wants to go down. That's a more egregious error, and so forth. The accumulated forces on just the bad I show here. And the question is how we actually compute these forces. So basically, we take a smooth function, a cost function, that penalizes, that's a function of the model scores, the current model scores, and it penalizes the ranking. So if you're to the left of this, the penalty is high if the score is different linearly, and to the right it goes to 0. Even if you have the same score, there's still a penalty pushing these things apart. And then we take that cost and we multiply it by the change in the metric you get by switching the two guys. And that's how lambda rank solves this problem of being able to optimize any information retrieval metric. So that's the key, and it gets around the differentiability problem by doing this after the sort. So here I've actually computed the forces for this particular example that you can see. The bad wants to go down on badly, and the perfect wants to go up a lot. So negative means come down, and positive means go up. So how do we actually go ahead with this? I've, again, shown the same URLs with their ratings on the left and the scores I just showed you, ranked by score. And those are the forces we just computed. And what we're going to do is we're going to take remember we're in the middle of training, we're going to figure out how to change the scores. So we're going to add a regression tree which takes all the forces attached to all the URLs for all the queries in the training set, and that's a large number of items. And it makes a split based on the features so as to minimize the variance of the forces that go either way in the leaf. So every URL travels down this tree, winds up in a leaf, arrange things so that the variance in the leaves is minimized. So for example, the red guy, that's great, minimum, small variance, they're all negative. The gray guy at the bottom, that's also good. So now we can add a little bit of these forces, depending on where the URLs land, to the original score. We'll do that now, and then reorder by score. And the bad has moved down one, that's great, we want it down. The perfect is stayed where it is, but its score has gone up, so we're headed in the right direction. And the forces have changed. So now we, again, model the new forces with another regression tree, and we repeat this. Reorder, new forces, regression tree, build a bunch of regression trees. That's how we rank. But I haven't told you how a split is computed, and this is the key. I've put here 4 of the features that we use today. They're all integers. We bin them. The circle is a node in the tree I've just shown you, and the red and the green are forces that I want to model. And the loss is simply a squared loss. It's the loss of each force, each y, minus the mean for the items that land in that node. And we want to choose a split. And to do that, we have to go through all the features, every column here, every value, compute the split, and find which gives the biggest decrease in the loss, so the biggest gain. And that's expensive. That's why training these things is slow, and that's what we sped up. So how do we speed that up? Well, if you look at these two losses and you subtract them, it turns out that the minimizing the loss is equivalent to maximizing this quantity, where the sum is over the forces that wound up in the left leaf on the left, and the size of the number of points that wound up there, and the number of guys that wound up in the right leaf and the points that wound up there. And that's expensive. But in fact, you only need one linear scan of the data to compute this if you form these histograms. So go through a feature, pick a feature, zip through it. First of all, you have to bin. This is critical. So you only get a small number of values. And this works because the data is very sparse. And if it's not sparse, it's sparse in the sense that it only takes a few values. They may not be 0, but it's sparse in that sense. Once you form these histograms, computing these sums is trivial and extremely fast, and you just sweep from left to right to compute them. So that's how FastRank, using boosted trees, became so much faster than the neural nets. And I'm going to stop there to give other people time to talk.
Thank you.
Thank you.
So Steve, so thank you, Chris. That's great. Let me ask you a question. Sure. And by the way, I'm surprising Chris with this. Now this is operating on the scale of the Bing search engine. In fact, this is the fundamental training regime for search quality in Bing.
That's correct.
And so, in what ways does that scale present new challenges or surprises for you?
There are two things that really matter. There's how fast it is to train, and the key there is just experimentation. We're looking for another factor of 50 or so by going to clusters and GPUs and so forth there. The other big challenge is essentially a cost in how fast you can generate these results. They have to be returned in milliseconds, so less than 100 milliseconds. So there's two issues, and there are things you can do about both of them. So
All right.
I hope that answers your question.
Great work. Thanks a lot.
Thanks, Peter.
Thanks a lot, Chris. So of course, for the public, it's hard to explain something like FastRank. But of course, in any demo that is based on a search technology, these things end up being very important. And the interesting interplay here between wanting to solve the mission of really accelerating the training regimen for a large search engine and that driving new computer science ideas, I think is really marvelous. Now, I'd like now to move from the mission-focused realm into the sustaining realm. And so these tend to be problems that don't have the same kind of time-critical aspect to them, but are reactive nonetheless. And so what's an example of this? Well, one thing that we do here in Microsoft Research is run a service called Microsoft Translator. And so if you've used Bing to translate documents or used Microsoft Office and used the Office translator or the Bing toolbar to translate a web page, you've used Microsoft Translator. And as this graph shows, the numbers, unfortunately, are proprietary, but a very large number of translation requests per day, really in the tens of millions, are served by this translation service. Now, this involves several dozen languages, natural languages, and that is a realm that requires tremendous amount of research in order to have continuous improvement, as well as the supporting context to gather as much training data as possible and to constantly drive new breakthroughs in machine translation. And so this is an example of kind of sustaining research where every day we have to make good progress in order to provide as much value as possible for all of our users as well as other researchers. But to get into a little bit more technical detail, I'd like to invite David Molnar to the stage to tell you about white box fuzzing. David?
Great. Thank you very much, Peter. Great. Thanks. So the problem we're talking about today is sort of a classic problem for Microsoft, which is that we support hundreds of different file formats across all Microsoft products. Every time someone external to the company finds a bug in one of those formats that lets a malformed file take over your computer, it costs Microsoft at least $1 million, and it costs you even more in the amount of pain and effort required to upgrade your systems. We want to stop this. And to stop this, we have a thing we call the security development lifecycle, which mandates testing for these bugs before any code hits customers' hands. Unfortunately, the most common kind of random testing can't catch the kind of bug you see on the slide, where a very specific relationship has to hold between variables in order for something to go wrong. Our approach makes use of state-of-the-art constraint-solving technologies we have at Microsoft Research, combined with industrial-strength binary analysis. And what that lets us do is it lets us watch programs as they execute on initial input. We see exactly what predicates they evaluate on that input, and we use this to come up with new constraints that, once solved, come up with new test cases, which then allow us to explore new parts of your program. And so Peter talked about sort of foundational, long-standing research. I mean, this idea of being able to write down a logic formula and determine if it's true or not, and if not, to find a counterexample, this dates back to Hilbert. But we now have one of the best solvers in the entire world, and I'd like to show it to you now in action on a real program. So we could switch to the demo thing. Yes, thank you. So what we have here is you have a little program. It compares the input bytes to B, A, D, exclamation point. And if this counter goes above 4, it crashes. That's nice. We're going to run it on the initial input good, and we're going to see what happens. So we type go Sage, and what's happening is right now Sage is executing the program on this initial input, and it's computing something that looks a little bit like this. So this is the output of Sage. It's looking at the trace of execution, and it's saying, I see that there's some kind of jump, so I'm going to add a new constraint. It then translates the constraint into an internal language, and later on it translates that into a sequence of constraints for Z3, which is the constraint solver developed by Microsoft Research. In this particular case, we can actually solve the constraints, and we can solve them very, very quickly, and we come up with a new test case. And in fact, we even have the ability to go look at the trace itself using WinDDG, which is a debugging facility in Microsoft Windows, and we can actually time travel and say, that's the exact jump that corresponds to this constraint that corresponds to this part of the program. And what this all adds up to is if you take a look at this results directory after a while, we end up sort of seeing that we have new test cases which are being created, which end up creating new parts of the program. And you can see it's creating GAD and bood and all that good stuff. And so eventually, we end up creating the test case, bad, which causes the program to crash, despite having told our program, Sage, nothing about this test. All it's done is watch the actual inputs and use it to create new test cases. Now, this is something that's a small test case, but we actually run on hundreds of different machines, and we have a system called Sagan, which keeps track of data from every single run. So every single time we run, we get data about what's happened and where it's gone. We can keep track of how it was run, all the test cases, and we keep track of statistics, which I'll talk about in a minute or so, that give us examples of where we're doing things right and where we're doing things wrong. So if we could switch back to the slides, please. Thank you. So the impact of this is that we've changed the way security testing is done at Microsoft. This slide shows you the relative number of bugs found in file fuzzing by the Windows Experience team during Windows 7. So there's hundreds of file reading parsers. And 1/3 of all the bugs were found by Sage. These are bugs that were missed by static analysis, missed by white box fuzzing, missed by human code review. And we're now running every Windows 8 milestone. We have ongoing engagements in Office and the Microsoft Security Engineering Center. And because of this partnership and this value we provide, we've been able to run for over 200 machine years and solve over 1 billion constraints, something we could not have done without the partnership of our fellows in the product groups inside Microsoft. But from a research perspective, what this does is it lets us ask questions that previously we could not answer because we just didn't have the data. For example, if we have several hundred programs all running on Windows, we can now tell you how much sharing they have in common. And this motivates research in how to reuse parts of our symbolic execution whenever we see different programs using the same piece of functionality. And then when we look at the solver, we now know that 90.18% of all constraints are solved in 0.1 seconds or less. And yet we know that the solving time still dominates as a group because there are millions and millions of constraints. And this gives us direct application to helping our colleagues in the Z3 world, who then help all tools inside Microsoft that use Z3. We build a virtuous cycle that keeps us ahead of the competition by answering questions that we could not have answered without this scale. And so to close, I'd just like to thank, there's a large list of contributors, but this is the kind of research why I came to Microsoft to do. This is the kind of thing where we have a deeply intellectually interesting problem of how do we look at the actual artifact of computer programs in the large, and we also have a deeply interesting practical application, which is protecting Microsoft customers. And this is the kind of thing that I love doing here at Microsoft. Thank you.
So thanks, David. That was great. Are you able to tell us of all the applications and systems that Sage gets run on, what tends to show up the most bugs?
There are certain parts of the...
Be careful what you say. Uh-huh.
Yeah, there are certain parts of display subsystems which are being actively worked on.
Okay. To be a little bit more serious, one thing I know about this area of research in Microsoft is that it's very, very deeply engaged with the academic community. Can you say anything about what's been important about that?
Yeah, I'd be happy to. So in terms of the academic community, we have a long list of publications on different aspects of the symbolic execution. But we also, there are a number of groups outside Microsoft, particularly Dawn Song's or David Brumley's. So Dawn's at Berkeley and David's at Carnegie Mellon, of course, who are actively working in this. So in fact, we were just at a summer school at MIT dedicated to applications of solvers like Z3. And we had several groups talking about this kind of symbolic execution at scale. So we were able to show them the data we had that we can show, and they were able to talk to us about their ideas. and we hope we can make our stuff better from that kind of engagement.
Yeah, and it's great that we give Z3 out to so many people.
Yes, it is.
Great. Thanks a lot, David.
Thank you very much, Peter.
Thank you.
Appreciate it.
Right. All right. So that's the sustaining area. And so let's continue to move around. So as we move out to kind of this open-ended long-term area, this is where I have a lot of affection. And I don't think it takes too much explanation here. I do want to point out that it's oftentimes the case that people equate blue sky or this quadrant with theory research. And that's really not the case. We're not talking about theory. We're really talking about really trying to push the boundaries of human experience and human knowledge and try to understand something new. And so what are some examples? Well, one example that goes on at Microsoft Research is in quantum computing. And in fact, in quantum, here at Microsoft, we taking a fairly radical approach in the work founded on Mike Friedman's research on topological quantum systems, or topological quantum computing, TQC. And so here, we're very, very interested in understanding whether there are practical physical realizations of so-called topological quantum devices. And if so, that would potentially drive different practical pathways to larger scale quantum machines. And so this is one example that is really trying to understand whether there's a new regime in quantum computing. And we take a fairly balanced approach looking at both the physics and computer science as well as the engineering of these systems. But enough about that. To get into a little more detail on a specific example for something really completely different, let me ask Nikolai Tillman to come here and tell you about programming on the phone. Nikolai? Great. Here's. Okay.
The world is changing. The way how we interact with computing devices is changing. So now more smartphones, devices like this, are being sold than traditional PCs and laptops combined. What does that mean? How do we use computing devices? What are we doing with our smartphones? We surf the internet, we play games, we read our emails. What are we not doing with them? We're not writing new programs on them. So they are incredibly powerful devices. The smartphone is much more powerful than the first computer I ever had. So my first computer was a big, clunky machine, very slow, horrible resolution. And yet, when I powered it on, it greeted me with a basic prompt. That is basically how I got interested in computer science and did my first baby steps in programming. And now the whole environment is turned around. What people get in their hands at first, it's a closed end-user device just for consumption. So we were asking ourselves the question, can we change that? Can we turn this form factor into a programming development environment? What I'm showing you now is an application developed for Windows Phone 7. It's available on the marketplace. So you can try it out yourself. When I power it up, what you see here is a list of scripts that are not just applications that you can run, but they're actually in source code. You can view the code, you can change it. So let's write a script together. So I click the Add Script button, and I can give it a name. Okay. And now I'm in a view where I see different actions. They're basically like functions of your programming language. Let's add a new function. And a function, an action, basically consists of statements. And you will see in a moment that it's very familiar to what you know. So let's edit this. Let's do an image search and display images that I find on the web. So I can go in and edit this statement. So instead of doing nothing, I want to do an image search. Now we are in a calculator view, which lets us edit expressions. And what I want to do is a search on the web. So here I can select web. And then using statistical analysis on existing scripts that people have written, we know that these are the most common actions that people want to do on the web. So let's do an image search, which appears in the list. And now I have to enter a string. Entering text is usually the most difficult aspect. In all other places, we really made sure that it's easy to hit all the buttons with a big thumb. Now I have to be a bit more careful. Let's search for Microsoft, and let's see if I can... No, I already misspelled. Microsoft. Okay. Let's go back. So this delivers us a list of pictures, and I want to do something with them. So I need to store them in a local variable. I can do that by pressing this orange bar. So now we introduced a local variable. Wasn't much typing. Let's go back to our list of statements. I have now a list of image links. Now I want to display them. So here in the statement level, I can add statements in a way that is structured. I cannot make mistakes at the statement level. So I can only choose now from a set of statements that make sense here. And I want to iterate over all the links. We automatically synthesize the variable link that we want to iterate over. And then what do I want to do with the link? I want to show it. And we are living in the Facebook age, so we call that posting to the wall. Each script has a wall output. It's an interactive version of the console. So that is a little script, a custom search I just put together. Let's run it. So now it's going to Bing, and it's getting images, and they show up shortly. Yeah. So here I have a number of images that I get from Bing, from Microsoft. I could show you more how to refine this program, adding if statements, but I want to show you a different program. So we currently have a high school student as an intern, and in just one day, he wrote a game, Gobbleman Tilt. So this game consists of more than one action. So I was just writing one now, but this one has a few more. And I will show you the code in a moment, but let's just run it. So I press the play button. And what we see now is a yellow guy who is moving around according to how I hold the phone. So this is using the accelerometer, which is measuring force or in general gravity if I don't accelerate the phone. And I'm currently running away from the bad guys, and now they got me. Now I got a score, and this score is automatically sent up to our server where we maintain a repository of high scores. It's very easy to program. So let's look at the code. What does it involve? So it involves creating a board, which is the grid you just saw of points that my yellow figure was eating. So how do we create a board? Well, there's a function create board, and then you see there's actually a number of instructions in here, but it's basically 2 pages of code to set up the board. It's not too much. And here you see that a matrix is being built of points. Those are the dots that my figure was eating. So there's a loop x, y, that creates ellipses and positions them all across the screen. And then later in the code, in update board, the code queries the accelerometer. Acceleration quick here gets the current, basically gravity coordinate, the vector, and it applies it as a speed vector to my figure that is here called PM. And then it iterates over all the enemies and makes a move towards this PM figure. So this again is basically 1 page of code, and a high school intern wrote it. Okay. With that, I go back to the slides. So we are very excited about this project, but you don't have to trust us. It's out there on the marketplace, and it's actually it's in the top 1% of more than 20,000 applications for the Windows Phone. So people really like it. Many people probably started to learn programming in this way now. So we have pretty good ratings. We believe that this is a great tool for teaching because it's a really engaging experience. So it's programming on the most personal computing device that the students have. And they can programmatically access all the songs and their pictures. I didn't show that, but basically in a loop, you can iterate over everything that's stored on your device. So instead of writing abstract algorithms, students can now sort their songs or let their pictures bounce around. So what looked very simple when I was doing it was, in fact, a lot of research trying to figure out what language and what editor is really amenable to this new form factor of a touchscreen. So in addition to the language and editor, it's also important that all the new sensors and access to the web is made available as a first-class citizens. So it's not just an added library on top of a legacy language, but all of these new elements of a smartphone are made available in a very easy way. If you want to see more, we have a demo over at the DemoFest. Thank you.
Thank you, Nikolai. So I have to ask, do you use your left thumb or your right thumb to do your programming?
I'm right-handed, so I use my right thumb.
Right thumb.
Yeah.
So more seriously, Just as someone who worried a lot about computer security when I was at Carnegie Mellon, are you worried that people might start making hacks and viruses on the phone now?
Yeah, but in a future version, we will enable sharing of scripts. So you could run a script your friend wrote, and maybe you have a malicious friend, and then it would send your contact information to Facebook, and maybe you don't want that.
Right.
So we are here in a unique position that we are designing a new language at a very high level. So we want to use automatic information flow analysis to ahead of time figure out what this program might do and put the user into the power to decide whether he really wants to run the script or not.
What a great thing. And just imagine all of the people who have as their only computer in the future a smartphone.
Yeah, everyone needs a phone. Everyone will have one of these. Yeah.
Great. Thank you a lot.
Thank you.
Thank you. So, programming on the phone, I have to say that struck me as a pretty blue sky idea. But in fact, as we see smartphones at this scale starting to really invade many parts of the developing world, the possibilities are really fantastic. Okay, so now we're down to our last quadrant here. And people who have come to know me here at Microsoft Research now know that I have a special place in my heart for the upper left quadrant. This is the so-called Disruptive Quadrant, where, roughly speaking, based on our understanding of the world today, what can be done that is surprising or disruptive? How can we change the rules of whatever game that we're playing? And this is something that I think many of us are always particularly tickled by, and that's true, and I think particularly true in computing research. And what better example of this than the recent excitement and the involvement of Microsoft Research in helping the development of the Kinect game controller. Now, one thing that, of course, when you have a Kinect, that's hard for the public to understand is that underneath the Kinect is decades of fundamental computer science and computer engineering research. Certainly, much more than a decade here at Microsoft Research, and the research here, of course, founded on research in the academic community that was even decades older than that. And so to give you a little bit of a glimpse of that, I'd like to ask Ivan Tashev, who really developed the technology behind the audio array of Kinect, to come here and tell you a little bit about it. Ivan?
Thank you, Peter.
Thank you.
Good afternoon. Before to start to talk about the technologies in Kinect, the first thing we did is actually to figure out who are our enemies. What are the factors we have to overcome so to make the audio part to produce enough good sound quality for speech recognition in telecommunication. And in this particular scenario, sitting in your media room, it happened to be the sound from the loudspeakers. Because, gamers, they tend to listen to extremely loud sound on levels which you can barely hear your own thoughts. The second factor, or group of factors, were sounds we don't know about. This is the room noise, which, when a person speaks at 3.5 meters distance, is pretty much comparable as energy with the noise, with the level of a human voice. So, at 3.5 meters, we have a 0 dB signal-to-noise ratio. And of course, this is the reverberation. We sit in a room and we speak, but only a small portion of the energy which reaches the microphones is so-called direct path, from our mouth to the microphone. A lot of the energy comes from reflections from the ceiling, from the floor, from the walls. And this is what smears the future of the speech signal, makes it less understandable, makes the work of the speech recognizer more difficult. And of course, we had to deal with enormous dynamic range of from loudspeakers, sound from the loudspeakers, to a soft voice of a kid, for example, at 4 meters. But still, in June 2009, when the work on assembling the Kinect audio processing pipeline started, we in Microsoft Research already had all of those technologies developed, published, patented. So for 1.5 years, the problem which we had to work on is to make those technologies to work well together, to assemble that end-to-end audio processing pipeline, to make each of the blocks to work better than what the state of the art is, and to create that critical mass of technologies, that explosive mixture, which later will become so successful project as Kinect was. So this is the block diagram of the audio processing pipeline in Kinect. The first several blocks, calibration and multi-channel acoustic echo cancellation, in general are designed to remove the sound from the loudspeakers as much as we can. Follows the beamformer and the sound source localizer, which are pretty much the microphone array processing, and a chain of additional speech enhancement blocks. So now we're going to go in each of those quadrants and to go in the deep details of the signal processing algorithms inside. I'm just kidding. So happened that for solving this particular problem, critical role played two of the blocks: the multi-channel acoustic echo cancellation and the microphone array processing. And I'm going to give you just a brief information about only those two. So acoustic echo cancellation is one of the oldest signal processing algorithms. It is part of every single speaker phone. This is the adaptive filter which estimates how much of the energy from the loudspeaker goes to the microphone, so we can subtract it from the microphone signal and have on the output just the local voice. Unfortunately, once we start to use the same approach with 2 channels, stereo, or 5 channels surround sound, the problems arise because those 2 or 5 channels are highly correlated. And this leads to ill-conditioned matrices and extremely difficult solutions, multiple solutions, and the system tries to reconverge constantly and has a reduced performance. And this is stereoacoustic echo cancellation is a long-standing research problem. What we did in Kinect is based on a simple logic. Because you have multiple solutions, because we have 1 microphone channel, 1 equation, and 2 transfer functions to estimate from the left and the right loudspeaker. So obviously, when you have 1 equation, we have to have 1 unknown, which means 1 adaptive filter. And then the normal approach is to see, okay, if we can have 1 adaptive filter, what it will be the mixing matrix, how we can estimate which portion of the left surround, and central speaker goes to the microphones. And for this, we have the famous calibration phase, which consists of playing of sounds like this. It sounds like a music, but actually is a highly sophisticated signal which contains every single frequency between 200 and 7,000 and 500 Hertz. This allows us to estimate the filters, the mixing matrix, and in real time, just to run 1 adaptive filter to compensate for open door, closed door, people move in front of the device. And the second processing block is the microphone array processor. So the logic here is simple. 1 microphone captures a lot of noise and reverberation. If you can have more than 1 microphone, and there are 4 in the Kinect device, if you haven't noticed it, they're positioned right here underneath the device. So there are 4 microphones, directional microphones, listening forward. And we utilize the fact that the sound wave reaches the device and the microphones in a different order. If someone speaks from this direction, the sound wave will reach the microphones in this order. On the other direction, it will reach in a different order. As a result, our sound capturing device has a sense of direction. So we can focus on a given sound source and suppress the sounds coming from other direction. This process is called beamforming, and it pretty much adds a special selectivity. In the upper right corner, you can see the directivity pattern of our microphone array when it is focused at 0 degree. So this is the frequency, and this is the direction. And we can see that the device actually can focus quite well towards the desired sound source. And in Kinect case, because we use so-called adaptive beamformer, we can do even more. When there is one sound source, an additional person talking, interfering sound source, the device can place actively a null towards that direction, which is the chart on the right lower corner. So here we can see that we have a sound source around here at 26 degrees and a competing sound source at -9 degrees. So the device places a null towards the undesired sound source, and we can receive a better sound from the desired sound source. Several quick demos. The first one will be how the Kinect device does sound source localization. Okay, 1, 2, 3 testing. So you can see that the device can sense 1, 2, 3 testing, testing, 1, 2, 3 testing. So the device can do localization and follow the sound source in the same way as when they do movie shots. And there is a sound operator with those long directional microphones and pointing the microphone towards the various artists. So a Kinect device does this completely automatically using the sound source localization and beamforming techniques. The second demo consists of parallel recording with the Kinect device and with the microphone in my laptop. For this, with your permission, I will try to switch off my microphone for a moment. One, two, three, testing, testing. And now we're going to see those two signals from a single microphone and from the microphone array. 1, 2, 3, testing, testing. So this is the single microphone. 1, 2, 3, testing, testing. So first, even in this quiet room, you can see that there is a substantial amount of noise, which we cannot hear because of the 2-element microphone array we have, and because of the 100 billion neurons processor we have between them. And once we start to do this system end-to-end, my last demo, it will show what happens in real conditions. So we have a gaming room with quite loud sound and a local person speaking commands. So this is what the microphones hear. And after processing,
Xbox shuffle. Xbox dashboard. Xbox go back. Xbox next button.
so the quality is not perfect, but it is sufficient for speech recognition. I did this demo only once with calibrated loudspeakers when the loudness in the room was actual loudness of 85 dB sound pressure level, and I was strongly advised not to do this anymore. So in conclusion, in Kinect we have three things which we haven't seen, at least well, in products out there. The first is this is the only product in the world with surround sound echo cancellation, which is a scenario enabling technology. The second, we do hands-free sound capturing. We don't have to wear a closed-talk microphone or any kind of headset. And the third is, this is the first open microphone recognition system. The speech recognizer is enough reliable, so we don't have to have a button to signal the computer I'm talking to. The keyboard Xbox does this for us. And at the end, why we're doing this? Because Kinect is nothing else but sensor for human-machine interface. It just adds two more colors to the palette of the user interface designers. It's a gesture and speech. And recent user studies with our beta users show that 54% of the users prefer voice modality when they deal with media for selection and for controlling their media player in their media rooms. And I would like to say that this is just the beginning of a nice and interesting journey. Thank you.
So, Ivan, really amazing stuff. So when a product group like Xbox comes and says, we want to be able to do clear voice recognition and hear clearly in a noisy room, in an arbitrary living room from a distance, what's your first thought? You've had a long history of academic research publishing in the area, but what happens when someone comes to you and asks you to work on something like this?
So for me, this happened in May 2009 when architect from Xbox came and said, Ivan, we need a couple of your technologies for a product you don't know about, but we're trying to put together. And then pretty much we started to put the technologies together.
So you didn't just run away.
I didn't.
Okay, very good.
Regardless of the fact that I was warned that this is not possible.
Thank you, Ivan.
Thank you, Peter.
Thank you. So we're almost out of time, but I hope you can see that, at least to my mind, what we do here in computer science, and I could have told a similar story like this at Carnegie Mellon or at DARPA. I suspect at any of your institutions and organizations, there's something special about computing research, that it blends the foundational and the applied, the near term and the short term. The same person is having a string of 12 years of seminal papers proving fundamental theorems in signal processing, and at the same time engaged in helping deliver a key part of something like Connect. And in all of these stories, we tried to show you the same thing. And I think it's something that's unique, really, to computing research, and we should all feel really lucky to be a part of this field. And so, to sum up, computing research, I think, has incredible diversity. The quadrants are really just my way of trying to express that diversity. But that is a wonderful thing that is important for us all, I think, to embrace. And don't fall into the trap of thinking that some people are basic, some people are applied. What is important in computing is that just about any practicing computing researcher really does it all. I know you all do, and so do we. And as you go to the DemoFest and see what goes on there, ask about the science behind the demo. I think you'll find it fascinating. So thank you very much. I really appreciated all of your attention. Great. I have been told that we are out of time for questions, and so let me promise that all 4 speakers and I will be in the DemoFest, and so we'll be happy to talk to any of you through the demos. Okay? Thank you.